The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay. So this is a fun lecture. This is the lecture where understanding the gradient, which we did last time, the divergence that we almost completed, those two pieces now come together into Laplace's equation. And it's just things work in a fantastic way. So I enjoy this one. So the result will be that we have the potential function u that we've spoken about and take its gradient. Then now is coming a stream function s that's connected with the divergence. When the divergence is 0, there's something called a stream function s. And the connections between those two functions, u and s, are crucial. And connecting gradient to divergence will take us to Laplace's equation. And then you'll see the special role of x plus iy in 2D. So this is in 2 dimensions. Okay, so let me begin with the divergence. This is the divergence of w, of course, and solve it. Just as we wanted to solve Kirchhoff's current law, A transpose W equals 0. So now in the continuous case, we want to find solutions to we want to find divergence-free fields, source-free fields, you could say. That's about the best word we have, divergence-free, meaning there is no divergence. Okay, so what have we got here? We've got one equation in 2 unknowns. Last time with the gradient business, we had 2 equations for u and only that one unknown. Now we've got 1 equation, 2 unknowns, because we're looking at the transpose. So now so there should be a lot of solutions, right? If you give me a W1, then probably I'll be able to find a W2. But there's a neat way to describe the solutions to that equation, the divergence-free fields. It's to introduce something called a source function, a stream function, okay? And now the idea will be that if I so I'll try, let me try. I take any function s of x and y, any function whatever. So now I try, let w1 be ds dy. So my, maybe I should say, maybe I should go this way. I'm looking for solutions, okay? So I take any function s, I take its y derivative to be w1. And you can tell me what w2 has to be. So let me see. So if w1 is ds dy, this will be what? This will be the x derivative of the y derivative, right? If w1 is the y derivative, then when I take the x derivative, I've got this cross derivative. So what would be the smart choice for w2? So I'll say then w2 will be, what will now I've sort of said what w1 is, what's the w2 that goes with it? Well, it's whatever it takes to cancel this. I want this to be, in other words, I want it to get 0, so this should be the second derivative of s, and what am I going to put now? dy dx. I'm using the same very crucial fact that the cross derivative can be in either order. So what do I see for w2? Do you see what w2 is? This is supposed to match that. There's a minus sign. w2 is what? Minus ds dx, right? Minus ds dx. That's the minus ds dx. If I take any function s, I let w1 be its y derivative and w2 be its minus its x derivative, then the divergence will be 0. because I'll have the cross derivative minus the cross derivative. Of course, that'll be 0. So these will be my W1s, my W's. W1, W2 coming from S. So I have what I expect. With 2 unknowns, only 1 equation, I've got lots of solutions. I create any function S, and that will be 1. So that's a stream function. And it has a physical meaning, so we get to see it. And it has a fantastic connection to the potential. When, so up to now, so this is now the moment the pieces come together. Up to now, we had the divergence and the gradient separately. So up to now, what we had was we started with a potential U, and we went to V. I called it V for this application, du dx, du dy. Okay? And now over on this side, I had the divergence of W equals 0. And that led me to W being what we've just said, ds dy, and minus ds dx. Okay, 2 separate pictures. Now we're going to connect the framework. We're going to give the connection between V and W. And the connection will be the easiest possible. They'll be equal. So the C in our framework is the identity. I want to look at our framework when C is the identity. So V and W are the same. In other words, what equation do we get then? We started with U. We take the gradient of U. That's V. We go over here, and we still have the gradient of U, because now this is the V, and now it's also the W. And then we take what do we take? Minus the divergence of the gradient of U equals, let's say, F. Should we say F to make something happen? Or 0? I'll say 0. I'll say 0. Yeah, because 0 is the one that gives Laplace's equation. The official name would be, that's Laplace's equation. Do you recognize it? We better write it out properly. The divergence of the gradient is the Laplacian. So this is Laplace. Famous equation. Steady state type of equation. It goes with steady state problems. Let's just figure out what this is. We've got, so W is, since these are the same, W is now du dx, du dy. It's the gradient. Now what happens, do you see what happens when I take the divergence of the gradient? The divergence of this W? What's the, what? I just want to write that equation out. It's crucial. I need brilliant colors and lights shining now for this, what goes in there. Because I want to take the divergence of the gradient. So what does that mean? I take the x derivative of the first component plus the y derivative of the second component. The minus sign is not going to matter with a 0 on the right-hand side. I could cancel the minus. So, but let me say it again. The divergence is, it applies to a vector. I've got a vector. I take the x component of the first, of W1. So that'll give me d second u dx squared. And I take the y derivative, I should have said derivative, y derivative of the second component. And the y derivative of that is d second u dy squared. And I get 0. So that's Laplace's equation. You see that the whole idea is Laplace's equation. In working with Laplace's equation, we have 3 elements here. The gradient comes in, the divergence comes in, and equality comes in. A more general, would you like to see a more general Laplace's equation? Well, a more general Poisson's equation. So let me, underneath Laplace, let me write Poisson. You got the pronunciation, the brilliant French pronunciation there of Poisson. That was my best. I can't improve on that one. Okay, so it comes in when there's a right-hand side. So the normal Poisson equation is second derivative with respect to x, second derivative with respect to y. Well, actually, our should have a minus there. Really should be a minus there just to. You remember why the minus is there. The minus is there to make the whole thing positive. I mean, right, that sounds crazy that the minus makes it positive. But these second derivatives are negative definite, as always, and the minus makes them positive definite. So I don't remember whether, maybe I often include the minus over here equal f of x and y. So there's a source. Poisson has a source term. Laplace doesn't. And just while I'm talking about this framework, if there was a c of x and y, so this would be or, I'll put or. The more general one would be the x derivative, because I'm taking the divergence, of a c of x and y du dx, and the y derivative of a c. So you see the difference. I'm now allowing some variable conductivity, variable whatever this, variable material, du dy equals f again. So that would be the more general one. I don't think we plan to study that in, well, that's not the most general. I could have more and more things there, but that shows you a variable material. Yeah, that material is variable. I would use the word, what word would I use? It doesn't depend on the direction. I'm using the same c of x, y in the x direction and the y direction, and therefore in all directions, and I didn't come prepared with that word. What's the word for when it doesn't depend on the direction? Isotropic, thanks. Isotropic. So that's isotropic, right. So that's really our framework there, at least for isotropic materials. And then we could have more general with anisotropic materials. That would be fun too. All of those things are fun. But Laplace's equation is the most fun of all. So let me take f to be 0, c to be 1, get back up to Laplace's equation, and begin to make connections. Begin to make connections. Okay. The beautiful connection. The beautiful connection is the one right here. When v and u are the same, when v and w are the same, then I just read off. If v is the same as w, then how is the potential function, which is on the left side, connected to the stream function, which is coming from any time div w is 0, I've got a stream function in 2D here. The connection is just those two match. Du dx is the same as ds dy, and du dy is the same as minus ds dx. You see what the two sides of our world are coming together. This is, we're dealing with flows that are both gradient flows. They come from a potential. And they're also, you could often say potential flows. I see the word ideal flows coming in. These are very special flows. You know, so arrow couldn't work entirely with these flows, of course. These are such ideal flows that, you know, proper aerodynamics, you've got shocks, you've got all sorts of stuff going on. But in a region of where everything's beautiful, then you get back to this set of total steady state, steady flow, steady potential flow. We've got those equations that connect u on one side with the divergence business, the stream function on the other side. So I want to focus on these. Actually, I mean, so the heart of Laplace's equation is in there. Yeah, okay. First, do you know the names of those two guys? I shouldn't call them guys. They're the greatest mathematicians ever, or maybe after Gauss. Do you know whose names are associated with those two equations? Well, Lagrange was great. I'm not saying anything about Lagrange, but he didn't do this. So one French and one German. So the French guy's name is Cauchy. And the German is, so these are Cauchy, and the German is really fantastic guy. Anybody know his name? Cauchy-Riemann. Yeah, the other name is Riemann. Cauchy-Riemann equations that connect the two pieces U and S. And they're the subject of an enormous theory that we'll just touch on here. Okay. And we'll see them graphically, and we'll find solutions. Yeah. So this is one way to pose our problem. Notice something here. So I think that if we have these equations, the solution U should satisfy Laplace's equation, because this equality will take us around the loop. So do you see that if I could solve these two, here's the point. I'm going to get Laplace's equation solved by U. Laplace's equation will also be solved by S, the stream function. So what's going to happen is I get two solutions, a pair of solutions. Laplace's equation, the solutions to that come in pairs, U and S. So we get them two at a time, and they're connected in this remarkable way. So why, let's see, can you see that U will satisfy, that this is the key to everything. Does U satisfy Laplace's equation? Sure, I take the x derivative of that, and I add to the y derivative of that. Do you see it works? The x derivative of this plus the y derivative of this is exactly the cancellation of the cross that I wanted. So I do these, I combine those into Laplace. Shall I just say that, go through that verbally again? I take the x derivative of this, which gives me the cross derivative of s. This asks me to take the y derivative, so I get the cross derivative again with the minus sign. They add to 0. I just want to point out that also s satisfies Laplace's equation. Can we do that one? I claim that also the stream function solves Laplace's equation, because we want the x derivative of ds dx. So ds dx is minus this. Do you see what's happening? When I take the x derivative of ds dx, I get minus the cross derivative of u. For this guy, it's the y derivative of this, which is plus the cross derivative of u. They cancel. So yeah, u and s are just together. Oh, let's find some solutions. They're great to find. Yeah, and then draw them. Okay. Can I find some solutions to Laplace's equation? And I'm going to find them in pairs. So I'm going to have a list of u's and their corresponding s's. Okay. These are solutions to Laplace. These are solve Laplace's equation. So we've got Laplace's equation in our minds. Actually, furthermore, they solve Cauchy-Riemann, because they're going to be connected by our Cauchy-Riemann equations. So solve Laplace and Cauchy-Riemann. Okay. Suppose I take u of x, y equal x. I'm going to start with an easy solution. That certainly solves Laplace's equation. You got Laplace's equation in mind. Let me write it up here again. uxx plus uyy equals 0. I take the chance to write it again to do it in this little bit shorter notation, just subscripts instead of partials. And also sxx plus syy equals 0. But most of all, the Cauchy-Riemann that connects the two. Well, does u equal x solve Laplace's equation? Of course it does. The second x derivative, if the function is x, is 0, and the second y derivative is very, very 0. Okay, so what's s? What's the s that goes with it? It'll be simple too. It's supposed to, so the s, so u is x, right? I'm starting with this x. So du dx is 1. So what do you figure s is? If du dx, see, u is just x itself, so du dx is only a 1. That derivative was easy. Then ds dy is supposed to be 1, and ds dx is supposed to be 0, I guess. Do you see what s is? Y. S is y. S is y. Of course, that solves Laplace's equation too, and it solves Cauchy-Riemann. The x derivative of this is the y derivative of that, 1 equal 1, and the y derivative of that is minus the x derivative of that, 0 equals 0. Okay, so that's an easy one. I'm going to go up a level. I want to take a second degree, so my next guy in the list will be a pair. It's a list of pairs. Will be x squared minus y squared. First of all, it better not be in that list unless it solves Laplace's equation. And then if it is, we'll find an s. So plug it in mentally. Can you plug this into Laplace's equation? What's the second x derivative of this function? 2, right? X brings down a 2. What's the second y derivative? Minus 2 from this term. And then put them into Laplace's equation. 2 minus 2, correct, 0. All right. Now I'm looking for the s that goes with it, the other one in the pair. Okay, so maybe I better think through what. So this is supposed to give me the s, du dx. So let me copy Cauchy-Riemann here, so we can just focus entirely on that board. So du dx, this is 2x in my example. Du dy is minus 2y. So what am I learning? ds dy should be 2x. ds dx should be 2y, because I have minus signs both there. What's s? Do you see s? The y derivative is 2x. The x derivative is 2y. And that stream function is 2xy, right? 2xy. Because the x derivative of this is 2y, and the y derivative of this is 2x. And we saw 2xy last time also. And of course, it solves Laplace's equation easily. Plug that in. The second derivative is 0. The second x derivative is 0. The second y derivative is 0. Everything. So that's a pair. This is a nice pair. Do you want to shoot for a third degree? We could maybe figure out third degree just by jiggling it. After that, we're going to need an idea, to get up to fourth degree. Let me try third degree. Cubics now. So I'm looking, first I just want to get somebody here. So it's some x cubed, and then I'm going to need some more stuff because x cubed by itself certainly won't work. I need something more, and I want to plug it into Laplace's equation and figure out what should it be. Okay, so when I plug this into Laplace's equation, what do I get? So let me do Laplace's equation over here to try to get the u of degree 3. So what's uxx so far? 6x, right? Bring down we get 3x squared, then we get 6x, so I've got a 6x, and I'm looking for, so uyy should be minus 6x to cancel that. So what do I want there? What do I need? I need a minus, I'm sure of that. So the second y derivative should be this 6x deal. What do I want? 3xy squared, that sounds good. Let me write it down and see if it is good. Okay, the second y derivative. Yes, we'll bring down a 2, and then the y's will disappear, and I'll have the minus 6x golden. Okay, that's great. That's great. Is that correct? I mean, it's great, but is it right? Yes, yes, okay. Now, You have faith that there's another one? Well, yeah, there is another one. I mean, right, there's Cauchy-Riemann never let us down. There will be a S that'll go with that. That'll solve the Cauchy-Riemann equations, and it'll look like it. And I think, and it sort of, I just sort of reverse x and y to get another one, because if I exchange x and y, I'm still okay with Laplace's equation. I think something like 3y x squared minus y cubed. You know, if that worked, then this one should work too, because I've just switched x and y, and I think it'll work right here. The second x derivative will be 6y, and the second y derivative will be minus 6y, and I think that's good. Okay. So we've got, let's put this list on hold for a moment. Some things, obviously, there's some pattern here that we've got to locate. Can I put it on hold for a moment and take, for example, the graph of this one, and I want to draw the pictures. Before I get a complete list, I want to draw the pictures of these functions. And what do I mean by pictures? I mean, draw the, so now I'm taking the u to be x squared minus y squared, and the s to be 2xy, and I want to draw I want to draw the vector field of the gradients of those guys. Okay, so this is the u, I want to draw the this is the potential, x squared minus y squared. So what are the equipotential curves? So this is now, I'm drawing the flow. And to draw the flow, I draw the curves on which the potential is a constant. X squared minus y squared equal constant. So what kind of a curve is x squared minus y squared equal constant? It's a hyperbola. It's a hyperbola. So let me put in, so x squared minus y squared equal, let's take 1, for example. As one constant. So x equal 1 will be on the curve when y is 0. And then what else will be on the curve? If x is a little bigger, like 2, yeah, what's the, if suppose, so here is 1, 0. That point is certainly x squared minus y squared is 1 for that. Suppose I go out to x equal 2. What should y be then to make this right? Where's the curve going? When x is 2, what is y? Square root of 3, up, plus, or minus. So square root of 3 is something like this, up or down. It's a curve like so. It's a hyperbola. And now if I change c to 4, let's say, then it'll go through 2, 0, and it'll go up this way. And if I change x to something very small, it'll still be, oh, do you know what there's a word, a Greek word, asymptotes. Oh yeah, what do I get if the asymptote is when this is 0? Yeah, when that is 0, what's my curve? What are x and y? They'll be the same. X will be y or minus y. I'll be on that straight line or on this straight line. So all these other hyperbolas are kind of asymptotic, whatever the word is. Right? Do you see them as a bunch of hyperbolas? And actually, more hyperbolas. Well, yeah, think. Let's see, back when I had a 1 there, I took x and y to be positive, and I got that hyperbola. But I could have, since I'm squaring them there, also these hyperbolas are here. So these same guys are on that side of the picture. Those are the equipotentials. So these are the equipotentials. Okay. Now, let me draw S. So those will be the no, I don't want to say equi-stream functions. That's awkward. So now I want to draw S equal constant, like 1 or whatever. So I've drawn this with a whole lot of constants, and now I want to draw the other guys. What do those curves look like? And what's their name? A curve on which the stream function is a constant has the nice name streamline. So now I'm going to draw the streamlines. And what are the streamlines? The streamlines will be the curves that the actual material flows. If you drop a leaf into this flow, it will, and you watch it, it'll flow along a streamline. And we can draw those lines. So what are those? 2xy equal 1, or the equation y equals 1 over 2x. That's also a hyperbola, right? That's also a hyperbola. This is a fantastic picture in which we have two sets of hyperbolas. We're second degree, that's why we're getting two hyperbolas. When I'm not going to tackle drawing, MATLAB could do it, draw the equipotentials and the streamlines for this guy. Oh, I'm willing to tackle this one. What are the equipotentials and the streamlines for the easiest one in the list there? Can I just draw that one? Because it makes a point very clear that we'll see when we draw these. Okay, so what's the picture, the corresponding picture? Here's the xy plane again. What are the equipotentials for this pair and the streamlines? The equipotentials are x equal constant. What are those? Those are lines, vertical lines. So the equipotentials are just vertical lines. Equipotentials, x equal a constant. And what are the streamlines? Horizontal lines. Streamlines go this way. And what's the great point about these? These are the streamlines, s equal constant. And of course, what do you notice here? They're perpendicular. The streamlines are perpendicular to the equipotentials. And why? It's because you remember we talked about what does the gradient mean? Which way does the gradient point? It points perpendicular to these equipotentials. And in this case, all these equipotentials are parallel, and the perpendicular lines are the streamlines, and they're all parallel. Now, over here, we haven't got straight lines, but we still have the beautiful figure. If I now I'm ready to tackle, I'll draw these curves. They're hyperbolas like y equal 1 over 2x. If I just make that y equal 1 over 2x, that's a line that comes down this way. Let me try to draw it. I'll use dashed lines. Of course, as x gets bigger, y gets smaller, but never, y never makes it to 0, because if y was 0, no x would work. So, but if I change that 1 to a 4, I've got a bigger, this is coming out here. If I change that to something very small, I'll get one that's coming. These are going, do you see how the picture works? These are all right angles. That's the great thing, right angles. 90-degree angles. Between the streamlines and the equipotentials. You may have seen this before, and now I just want to ask you why. Why are those 90 degrees? We kind of see it physically, that the gradient is the flow is in the gradient direction, and we know that gradients are always perpendicular to equipotential lines. The gradient of any function is perpendicular to the level curves. That's all we're seeing here. But we're seeing these two fantastic families of curves, equipotentials perpendicular to streamlines. And the reason they're perpendicular is Cauchy-Riemann. Cauchy-Riemann is telling us they're perpendicular. Because the gradient, you see that they're perpendicular, and it's maybe overkill to try to give a proof. The gradient of u, what I want to say is that the gradient of u is a 90-degree rotation of the gradient of s. Let me put it that way. The gradient of s, the gradient of u, rotate 90 degrees, rotate gradient of u by 90 degrees, pi over 2, and you get s. You get grad s. That's what these equations say. That if I take the gradient of u, let me try to do that. So I take the gradient of u, that's du dx du dy. So if I have a vector in 2D, du dx du dy, and I want to rotate a vector by 90 degrees. What's the result? Suppose I have a vector AB, and I'm looking to rotate it. What's the vector that goes that way? If that vector is AB, that vector should be what? You may not have done this, but it's worth just noticing, and you won't forget it. It's got to have a zero dot product, right? So I'm looking for a vector here. This went out A and up B. I'm looking for a vector there that's perpendicular to this vector. So what should it do? What am I going to put there? A B. And what am I going to put? Oh, no, it went backwards, sorry. When I put there, I should have put minus B. And what goes there? A, yeah. That's the perpendicular one. Right? If that's the 90-degree rotation. And that's what Cauchy-Riemann is doing for us. I take the gradient, I take this vector. Now I rotate by 90 degrees, means I reverse these, reverse a sign, and I've got the gradient of s, or minus the gradient of s. I won't say whether the rotation is plus 90 degrees or minus 90 degrees. This can remain an exercise to see it slowly and clearly. I'm happy if you see it in the picture there, and of course you saw it in this picture here. So this is a moment then to take a little pause, because we've got 10 minutes for the great event. We've got the general idea. The u equal constants and the s equal constant. These two families of perpendicular curves, one telling us where level sets for the potential, the other telling us the direction of the flow. The flow goes perpendicular to those level sets. It's just wonderful. And now I would like to get the pattern that's going on here and complete that list. Okay. Well, that pattern comes out of the blue, I have to admit. You might sort of recognize it, that something, here's obviously stuff to the first power. Here we've squared something to get here. Here we've cubed something. You sort of recognize these numbers, 1, 3, 3, 1, or 1 minus 3, whatever. We're taking powers of something. And that something is what comes out of the blue. It's this quantity x plus iy. Complex variables. Everything here was real until this moment. And then I'm saying that the complex number I, the imaginary number I, the square root of minus 1, which of course it just Whatever, I mean, it's not a real number, but it has the property. Whenever we see I squared, we write minus 1. So then we know how to deal with it. Okay, sort of. Anyway, so that complex number I'll call Z. And here's what I think. I think that these two pieces are the real and the imaginary parts of Z. Now, these two pieces are the real and the imaginary parts of Z squared. These two pieces will be the real part and the imaginary part of Z cubed. And if we check that, and then we begin to see why should these satisfy Laplace's equation, we'll have the whole pattern. It'll just be x plus iy to 4th power, 5th power, 6th power. We can make a complete infinite list of pairs of solutions to Laplace's equation. So can I just see, let me just check what I said about the squares first. How do you do x plus iy squareds? Because that's what I believe we're seeing in the quadratic list. So I claim that if I take x plus iy squared, just do it normally, I get x squared, and I get 2i xy's, and I get I squared y squared, right? I just squared it, following normal algebra rules. Now, what's the real part? What's the real part of this x plus iy squared? X squared, this is real. And this is real because I squared is minus 1. This is minus y squared. That's our guy. And the imaginary part is 2xy. That's what the imaginary part is the part that multiplies I. So by some magic that we'll next time is the fun of exploring this magic, we get solutions to a real equation. We get two solutions to a real equation by working with this complex thing x plus iy and taking things like, now if I go to x plus iy cubed, well, let me just say it'll work. We'll have, you remember when it's like, if you cube something, you're going to see 1, 3, 3, 1. You'll have an x cubed and a 3 x squared iy, and a 3x iy twice, and a 1 of the iy cubed. And then you look to see what part is real, and you say x cubed is real, and I squared is the minus, so I have minus 3xy squared golden. And you look for what part is imaginary, and you see the 3x squared y, and you see the I cubed. So what's I cubed? Is minus I. So that's an imaginary term with a minus that we wanted. So now we've got the whole thing. We've got solutions to Laplace's equation coming from all the powers. And that, this is now the moment to celebrate, right? Because we've got a giant family of solutions to Laplace's equation. We've got the real parts. So U is the real part of x plus iy to any power, and S will be the imaginary part. And I claim that just as we held for n equal 1, 2, 3, for every n, these will be solutions to Laplace's equation. They'll, not only that, they'll be connected by Cauchy-Riemann, so they'll be the potential and the stream function for a flow, and we've got lots of them. And well, we got even more because we have linear equation here. So what are we allowed to do? If we have solutions to a linear equation, what are we allowed to do with those solutions to get more solutions? Combine them. I can take any combination of these guys. I can take or, so and, or, I don't know which to put, or, and. The real part of any combination of these. So I could take a combination of, I can take coefficients ck, or cn, maybe I should say cn, x plus iy to the nth. So if I take a combination of solutions with coefficients cn, I still have solutions. And what will be the twin solution, or the stream function that goes with this u? So this is another u. This is a really virtually a complete family of u's, because we have all these coefficients to choose. And what will be the s? So what's the corresponding s then? It's the imaginary part of what? The same thing. The same, we're just taking that same combination of the special ones. So the special ones were x plus iy to the nth, and the combinations are those. Yeah, these are fantastic solutions. And now, since I'm blessed with 2 more minutes, I get to make them much easier. Because already when I got up to x cubed and y cubed, they're looking messy. You say, okay, great to have all these solutions, but how am I going to use them? You know, they're getting more and more complicated as n increases. But switch to polar coordinates. Make the same list in polar coordinates. So again, I'm just going to list the same guys in polar coordinates r theta. Then you'll see then the pattern really jumps out. So what is x in polar coordinates? If I switch from xy rectangular coordinates to r theta polar coordinates, x is r cos theta. And y is r sine theta. Okay. Well, so far it doesn't look any easier. X and y look fine. But let me go to the second one. So this is now r squared cos squared theta, right? Minus this is r squared sine squared theta. Trigonometry comes in. I have r squared cos squared theta minus r squared sine squared theta. I want to simplify that. So it's got an r squared, and it's got a cos squared theta minus sine squared theta. Anybody remember that? Cosine of 2 theta. And this one. Well, what do you think is coming? What do you think is coming here? I have 2 r cos theta times r sine theta. I've got an r squared, again, times 2 cos theta sine theta. So what's 2 cos theta sine theta? Sine 2 theta, you get it. Sine 2 theta. And you know what's coming next, right? You know that now the whole family in polar coordinates, what's the nth power? What's the nth? We can now write down the nth one in this list. It is r to the nth, or the nth pair, r to the nth times cos n theta, and r to the nth sine n theta. So those are the twins, the u and the s, that we get if we use polar coordinates. So that's just terrific. Now we have a whole lot of solutions to Laplace's equation, and we have, don't forget, all combinations of them, and we're really ready to go. So Friday we'll be solving Laplace's equation in the cases that we can do it, by pencil and paper, by chalk. And then after that comes solving Laplace's equation by finite differences and finite elements.